Yeah. Hello everyone. So it's Harish. I am a PhD student at ISER Mohali, and I'm going to conduct your this last live interaction session for Algebra 1 course. So we have already seen the we have already discussed uh, assignment 1 to 11 of last year's course, and now in the week 12 interaction session we are going to discuss some problems from last year's assignment number 12. So yeah, let's begin. So 12, right, so we are going to discuss uh, assignment 12, and that is of previous years. Okay. Okay then. So I'm pasting the first question. The first question is a very easy one, which says what is the order of the group Z mod 2Z direct sum with Z mod 3Z, sorry, Z mod 6Z. So you all uh, must be aware of this group, and you can quickly say that what is the order of this group. So I'm not going into the details, but because it's very straightforward. The order of A is, as it is direct sum, so it is definitely the uh, product of order of its individual components. So it's just order of Z mod 2Z dot order of Z mod 6Z, and that is 2 into 6, which is 12. So it's a very easy question to start with. There is nothing special in this. It's a very straightforward question. So I hope this should be clear to everyone. Now we are going to see the some more interesting problems. So let me just copy paste the second question. Okay, yeah, here it is. So it says which property ensures that the algorithm to reduce the first entry A11 of the matrix A11 of the matrix A over a PIT. So to calculate the split normal form, we were trying to reduce the entries. Uh, what we were intended to do, we were first making all entries in the first row except the first entry to be 0, and then after that we were intended to reduce to make all entries of the first column except the first entry to 0, and in this process we were also reducing the first entry uh, A11, and the question says that what guarantees that that process of reducing terminates after a finite number of steps. So as you can see, they have mentioned that uh, it's a PID, not necessarily Euclidean. So all Euclidean domains are PIDs, but the converse is not true. So they are mentioning that you have to uh, answer it considering that it's not a Euclidean domain. So for Euclidean domain, we know that so for Euclidean, uh, uh, just a minute. Yeah. So for Euclidean domain, what is the property that helps us in uh, confirming that it will stop after few few steps? Yes. So in case of Euclidean domain, uh, the property is mm, or I should write like that. The property precisely the degree function ensures the termination of the algorithm after finitely many steps. But if you are not in a Euclidean setup, if you are in a PID setup which is not Euclidean domain, then the degree function has no meaning because it's not necessary that the PID is having a degree function. It's for Euclidean domain. So for PID, what is the property that guarantees? So if you remember the algorithm, then for PID, let's say your matrix A is this A11, A12, so on to A1n, and then A21, AN1, and dot like that. So for PID, the algorithm uh, provides us an ascending chain of ideals. And as it is a PID, so you can also say that ascending chain of principal ideals. Principal ideals. Okay, and definitely the ideal will start at A11, then you have some numbers say R1, R2, and an ascending chain of ideals. And then if you want to terminate this algorithm in a finite number of steps, then this ascending chain of ideals must terminate, and that is guaranteed by the Noetherian property. So the Noetherian property ensures the finite step termination of this chain of ideals. This is of course an ascending chain, and thus it ensures the finite step termination of the algorithm. Okay, so it's the Noetherian condition that ensures it. So let me just revise it for once. So it's the question says which property ensures that the algorithm to reduce the first entry A11 of a matrix A over a PID, which is not necessarily a Euclidean domain. All Euclidean domains are PID, but the converse is not true. So they are saying that if you are given a PID, which is not necessarily be a Euclidean domain, what condition on this R ensures that the algorithm terminates in finite number of steps. So for Euclidean domain, the degree function ensures the termination of the algorithm in finitely many steps. But as we are given that the PID need not be Euclidean domain, so for PID, uh, the algorithm it changes and the algorithm provides us an ascending chain of ideals. If you can look at this algorithm in I think lecture 1 or 2 of this week's content, and then this uh, chain of ideal terminates due to the Noetherian property of the PID. So Noetherian property ensures that the ensures the finite step termination of this chain of ideals, and thus it ensures the finite step termination of the algorithm. So option 2 is correct. Okay. So second option, that is Noetherianness. What is Noetherianness? Okay, this option is correct. Okay. Noetherianness is correct. Okay. So I hope it's clear. You can have a look at this question for a while, and till then I will just paste the next question. Okay. So if there is no doubt, then we can move to the next question. So yes, it says let omega be this complex number 1 plus root of minus 19 by 2, and z omega is a non Euclidean PID. So z omega is just, you can consider it as a ring of polynomials with integer coefficients and uh, ring of polynomials in omega with integer coefficients. Okay, so that is z omega, or you can also say the smallest ring containing omega and all integers. Okay, both definitions are absolutely correct. So that is z omega. So it's a non-Euclidean PID. So you can check that. The proof it's not that much straightforward, but for the sake of the question, you can just believe in the statement that it's a non-Euclidean PID. Now it's saying that calculate the Smith normal form of the matrix. This matrix they have given, and for that one property of omega you can use is omega minus omega square is equal to 5. So there have been four options given. Now, first of all, see in this even in this setup, z omega, after imposing this condition omega minus omega square equal to 5, the first thing you can check is all four options are represent distinct element of z omega. See, if these two are same, then omega has to be same as omega square. The first two entries are exactly same, and the third entry is differing. So these two has to be same, omega and omega square, but that will imply that 5 is equal to 0, which is not true in z omega. These two are different, and uh, if this matrix is same as this matrix, or this matrix is same as this matrix, then omega minus 1 has to be omega, and that will impose that minus 1 is equal to 0, which is also not true. So this matrix is also differ from these two in z omega, and the third matrix that is omega square minus 1. You can also see that this matrix is also uh, not same as these three, even if after imposing omega minus omega square equal to 5. So it is not same as all these options are different in z omega, and as you know that the Smith normal form of a matrix is unique. So at least first thing is clear that only one option is correct. Okay. So because here in all questions it is not specified that whether it is MCQ or MSQ, so you have to check all the options, but this much should be correct that only one of them is the correct choice. Okay, so if you find a correct choice, then definitely all three other options are incorrect. So let us try to calculate the Smith normal form explicitly, because that will also clear your all doubts regarding Smith normal form. And it is, instead of guessing that which is Smith normal form using the properties of it, it's better to calculate it. Okay, so let me just write this matrix again, because I think you might not be able to see the matrix now. Okay, so the matrix is, you can just copy paste from here. Let me just write. So it is 1 minus omega, omega minus 1. Option is 1 minus omega, omega minus 1, and 2 omega, 8, omega 4, 2 omega, 8, omega 4, then 8 omega plus 7 and 3 omega plus 2. 8, 8 omega plus 7 and 3 omega plus 2. Yes. So uh, now what is the process of converting it into a Smith normal form? First is to make the all entries of the first row except the first entry, all entries of the first row to be 0, and for that we can use the row operations and column operations, except the fact that accept the operation of multiplying a row or a column by a non-unit. Okay, so you can apply all row operations and column operations, but you can't do like that. like R1 going to 5 of R1, this is not correct because 5 is not a unit here. So this kind of operation, or C1 going to say 2 of C1, this you can't do because this is not allowed. All other row operations and column operations you can do. So let's first try to reduce this entry, the second entry of the first row to 0, and
Sir,
get how. Yes,
uh,
Ravi.
you said, sir, 5 is not a unit. What does that mean, sir?
Uh, 5 is not invertible here, Z omega, right? There is no inverse of 5 in Z omega.
Okay. Oh, yes, sir.
Unit means the element which has multiplicative inverse. Okay, so you can do like that, that R1 going to minus of R1, because minus 1 is a unit. Inverse of minus 1 is minus 1 itself. So that you can do. Okay, so now let's see. So we want to make this entry to be 0. So for that we can simply use this operation. R2 is R2 plus omega of R1. Okay, that will definitely make R2 to be 0. Oh, sorry, it should be in C. So column wise, C2 going to C2 plus omega C1. The first column will be as it is. The last column will also be as it is because there is no change made in it. And I recommend you to do one operation at a time because that will reduce the chances of error. 3 omega plus 2, and only the changes in the second column. Second column is second column plus omega times the first column, minus omega plus omega, that is 0. So it is 0. 8 plus 2 omega square, that is 2 omega square plus 8. 4 plus omega square, let me write it like that, omega square plus 4. Okay, so we have made the second entry of the matrix to be 0. Okay, so now let us try to make the third entry, that is this entry, to be 0. And for this also we will follow the obvious step, that is C3 going to C3 plus omega minus 1 of C1, right? Oh, sorry, not plus, it should be minus, right? So omega minus 1 minus omega minus 1 times 1, that will be 0. So this entry will become 0. Okay, and here, uh, okay, rest two columns will be, there will be no change in it. Let me just quickly write them as it is. And if you 8 omega plus 7 plus omega minus 1 times 2 omega. So if you do it, it will be, you can check, just minus 2 omega square plus 10 omega plus 7. And the last entry will be minus omega square plus 4 omega plus 2. Okay, it's not that much clear, so let me just write it again. It is minus omega square plus 4 omega plus 2. Okay, so all entries in the first row have been made 0 except the first one. Now it's done for these two entries to make it 0. Okay, so then for that we have to apply the row operations, and This to make this entry 0, what we should do? We should just apply this operation. R2 is R2 minus 2 omega of R1. Okay, and uh, first write it and then I will make the matrix. So the first row will be as it is, 1 0 0. In the last in the second row, 2 omega minus 2 omega 1, that is 0. And this will also be as it is because the R1 and corresponding R1 entry is 0, so it will won't affect it in any way. So and this will also be as it is, plus 10 omega plus 7. And the third row will also be as it is because we are not making any change in it, minus omega square plus 4 omega plus 2. Okay, so this is the matrix that we will get. Okay, now we need to make this entry to be 0. So I will write this uh, in the next page. But the operation you can see is R3 going to R3 minus omega of R1 that we can use. Okay, and the matrix that we will get is, the first row will be as it is, no issue with that. The second row will be as it is, we are not making any change in that. In the third row, first entry will be 0, omega minus omega times 1. Second and third entry will be as it is because the corresponding entries in first row is are 0. Okay, so we minus omega square plus 4 omega plus 2. So that is the first crucial step that we have done. Now it reduces to a 2 cross 2 matrix, 2 cross 2 sub matrix. Again, the same process will we will follow, but uh, you can see directly that omega square plus 4 is just half of this 2 omega square plus 8. So let us make this entry directly 0 using this. Okay, it is very easy to do that. So I will just follow this. R3 is okay. Mm, or we can do something. Instead of making it 0, we can make this entry to be 0 and then we will interchange the rows if required. So R2 is R2 minus 2 times R3. Okay, so first entry will be as it is, 1 0 0. Second entry, this 0 won't be affected, and this 2 omega square minus 2 times omega square plus 4, this will become 0. Now calculation you need to do here. Here you, if you calculate it, it will be omega 2 omega plus 3, and it will be 0. It is omega square plus 4, and here you have minus omega square plus 4 omega plus 2. Okay, and let's get rid of this omega square and minus omega square as well. Okay, so we can just do, but see, before that, this entry here we should have a non-zero term because in the Smith normal form, we try to diagonalize it. Okay, and so this diagonal entry, if let's first make it just interchange C2 and C3 so that this 0 is sent to the right place, that is this side. Just replace C2 and C3, that is also allowed here. So the first uh, or if you want you can do the R2, you can also interchange R2 and R3, that is also fine. Okay, so but there won't be any change in C1 if we apply this. C2 and C3 will be interchanged. Let me just write the interchanged values, and this will be 0, 0, omega square plus 4. Okay, now look at this submatrix we have made. The in this submatrix, except the first entry, just focus on this submatrix. Okay, in this submatrix we have made the all entries in the first row except the first entry to be 0. Now our task should be to make this entry to be 0. Okay, right? So we will now focus on making this entry to be 0, and for that let's get rid of this omega square first. So if we do that, then this C2 is C2 plus C3. See, during the entire step, try to maximize the number of zeros. Don't put a condition which increases the number of non-zero entry. Sometimes you have to do this because there might not be any other option, but the process uh, terminates easily if you increase the number of zeros. Try to maximize the number of zeros. Okay, so that should be in your mind. So the first column will be as it is, that is uh, 1, 0, 0. The second column will be the sum of first and second and third. So this will be 2 omega plus 3. If you add second column to the third, this entry will now be 4 omega plus 6. And this is 0, 0, omega square plus 4. Okay. Now, can you just guess how to make this entry to be 0? Ravi, any idea?
Uh, sir, these are multiple, not into 2.
Yes. So we can just do R3 going to R3 minus 2 of R2. Okay. तो पहली रो as it is रहेगी, that is 1 0 0. Then second is 0, 2 omega plus 3 0, and third minus 2 times R2 is 0 0 omega square plus 1. So this is your Smith normal form. Okay, the final Smith normal form is this, but you can see it is not matching with any of the option. Okay, so that might happen. So we need to change it to the desired form. But okay, but Smith normal form has one more condition, that this D1 should divides D2 and this D2 should divides D3. So is it happening? We see 1 will divide 2 omega plus 3, but we don't know whether 2 omega plus 3 will divide omega square plus 4 in the given ring. So we need to simplify them a bit. So for simplification, you can just do the rough calculation that 2 omega plus 3, it is, you can write it as 2 omega minus 2 plus 5, right? So 2 can be taken common, omega minus 1, and 5 was omega square minus omega minus omega square, sorry. So it is omega minus omega square. So this is omega minus omega square. So here also you can take this omega common, and it will be minus omega common. It will be uh, omega minus 1. Yes. So this is 2 minus omega and omega minus 1. Okay. And what is, or this is minus of omega minus 1, omega minus 2. Now for omega square plus 4, you can simplify it like that. Add, this is omega square plus 5 minus 1. 5 is omega minus omega square. And then you have minus of 1. From omega square get cancelled, and it is just omega minus 1. So omega square plus 4 is omega minus 1. So this matrix is equal to this matrix. You're just using the uh, condition over omega. This is 0 minus omega minus 1, omega minus 2, 0, 0, 0, omega minus 1. So this is not a Smith normal form still, because this entry is dividing this, but this entry is dividing this, not the converse one. This should divide this. So we should interchange their position, and for that we have to apply some more operations. So first let us interchange R2 and R3. If you interchange R2 and R3, you will get 1, 0, 0, 0, 0, omega minus 1, 0 minus omega minus 1, omega minus 2, and 0. And then you need to change this C2 and C3 so that you get diagonal entries. So it will be 1, 0, 0, 0, omega minus 1, 0, 0, 0, minus omega minus 1, and then omega minus 2. Okay. So first thing is clear. Okay, still
Yes.
this option is looking similar, but there is some minus here in our final answer. Okay, but there is no minus in this option. So, but I told you that you can multiply the rows and columns with some units, and minus 1 is a unit in this ring. So uh, now you have to do another operation, that is C3 or R3, anything you can pick. C3 going to minus of C3. Okay, so that is allowed because minus 1 is a unit here. That will be 1, 0, 0, 0, omega minus 1, 0, 0, 0, omega minus 1, omega minus 2, and certainly 1 divides omega minus 1, and that divides omega minus 1, omega minus 2. So this is your Smith normal form, the final Smith normal form. This is also a Smith normal form. Uh, Up to units, it's okay. Okay, this is also a Smith normal form, no need to worry, but up to units, it's unique. Units may differ. Okay, this is your Smith normal form. So option, this option is correct, the third one. Okay. Yeah, Ravi, any doubts?
No, sir, got it.
Okay, so it is clear. So let's move to the next question. So next three questions are based on computing the column space and modulo it with the uh, metric space. Sorry, the original vector space. I will just paste it. Okay. So it says for which of the following matrices the column space is Z square modulo the column space of A is infinite. Okay, so let me just quickly tell you the definition of column space, although it has been discussed many times in the lectures for the sake of revision. So column space of A is just, you can say, the range of A, that is A of V, such that V is belonging to the space. Space is Z square here. Okay, and this Z square space is considered as the column vectors. Okay, space of 2 cross 1 column vectors over Z. Okay, so now we need to first compute the column space of these matrices and then modulate with Z square. You can directly go with these matrices A, try to compute their column space and then modulo it with Z square, but that is very tedious process, and it will also have a lot of errors. Okay, so I'm going to tell you a small trick uh, for computing this quotient space. You can also go with the same approach, like you know what is matrix A, you know the definition of column space of A. Now you can compute it by using the definition directly and then try to modulo it with Z square, but that will lead to that is not an easy thing to do. Okay, and that uh, might confuse you in many occasions. So one uh, statement or theorem you might have seen, or one lemma was proved in the lecture. It's also that I'm just stating it as it is. That if x and y are two matrices mm, in say m cross n, and such that x is equivalent to y. Okay, this means equivalent, and equivalent definition is just there exists some matrix in GLMN R. R is a ring, commutative ring, not your real numbers, and B in GLNR such that Y is AXB. This is being equivalent mean. Okay, these things all being discussed in the lecture. I'm just revisiting these definitions. So if these two are equivalent, then Rm modulo the column space of X is isomorphic to Rn. Oh, okay. Mm, Rm, the column space of Y. Okay. So yes. Or as we are in square matrices, so we can also assume that M and N are same. It will reduce the confusion. Let it just be M cross M. Okay, so there is just this in GLM R, and this is also in GLM R, such that Y equal to AXP. Okay, so what does this mean? That it is you can compute the modulo column space for an equivalent matrix. It is not necessary that you compute the column space for this matrix only. You can compute the column space of any matrix that is equivalent to this matrix, and that column space uh, modulo your original space will give you the same space as this matrix A is giving you. Okay, is this clear?
Yes, sir.
Okay, so and the second lemma is, if the Smith normal form of A is, let's say, AS, then A is always equivalent to AS. Okay, so whether you so these two are equivalent. So whether you compute Rm modulo C of A or Rm modulo C of AS, they will give you the same column, same space. So uh, you can do the computation with the Smith normal form, that is AS. And Smith normal form is just a diagonal matrix with sufficient amount with zeros in the lower diagonal if it is. Okay, Smith normal form is of this form, and it is easy to compute the column space for diagonal matrices. And once you know the column space explicitly, you can directly modulo it with your original space and get the answer. Okay, but for a non-diagonal matrix, it's not easy to compute the column space. So that's why for this kind of question, I will suggest you that first compute the split normal form of these matrices, and then try to see the column space. Okay, so let's do these things. So for the first example, we will compute the Smith normal form. The first is 5523. Okay, so 5523. So we should make this entry first to be 0. This is exactly same, so we can directly do this uh, R, C2 is C2 minus C1. So that is C1 will be as it is 5, 2, it will be 0, 5 minus 5, 3 minus 2 is 1. Now the second thing is to make the first entry of the second row to be 0. Okay, this entry we want to make 0, but 5 is bigger than 2 in this ring, so we should interchange it. Okay, as per the algorithm, we should interchange this first, so that we will do R1 and R2 must be interchanged. So because we need to put the smaller number at at first. Okay, so okay, this is 2150. We are interchanging the rows, 2150. But okay, now let's try to make this. Or did I do anything? Okay, so for reducing this, remember we can't write fractions, like we cannot do that R2 is 2 by 5 of or 5 by 2 of R1. Fractions are not allowed because that they are we are in Z square setup. Okay, so but let's try to reduce this 5 as much as we can do. So we can use this. R2 is R2 minus 2 of R1. See, as I told you that we will try to increase the number of zeros, but in some stage we need to somehow differ from it, and this is the stage because we need to first reduce the value this 5 in so that this 2 and 5 become multiples, 2 and this entry, whatever entry we get. So in this process, this 0 is being removed. So the first row will be as it is. The second row will be like 5 minus 4, that is 1. 0 minus 2, that is minus of 2. Yeah, now you can try to make again this 1 is there and 2 is there. So you have to interchange this. It should be R1 interchange with R2 because 1 is smaller. Smaller entry should come first. It is 1 minus 2, 2, 1. So now this entry is also multiple of 1 and this entry is also multiple of 1. So you can make these entries 0 easily. Okay. So let's try to do it. Okay. How to make this minus 2 0? That is just C2 is C2 plus 2 times C1. C1 will be as it is. This is 0, 1 plus 2, that is 5.
Sir, here 2 is unit, no? 2 is unit element.
2 is not a unit in Z square. In Z square, 2 is not a in Z, your underlying ring is Z. All these elements you are taking from Z. So in Z, 2 has no inverse, right? R में inverse होता है उसका. Is it clear, Ravi?
Yes, sir.
ठीक है. It is saying Z square modulo 2C1. We need to compute. That means the underlying ring is Z, not R. Okay. If you would have asked R square modulo C of A, then we would have uh, used fractions also, and then 2 would be a unit, and all these things will go. But here we can't do that like that. So this is 0. Then for R2, it should be R2 minus 2 times R1. So it will become 0.
Sir, then we are doing 2C1, no? C2 plus 2C1.
Yeah, that we can do. That we can do. We cannot do like this. Multiplication we can't do. We cannot do R1 or C1 going to 2 of C1. That is not allowed. But linear relation is allowed. Okay. It is C2 going to C2 plus 2 C1. That is okay.
Okay, sir.
Okay. You can't multiply something to directly to C2. Like you cannot do like that. C2 going to 2 C2 is not allowed. But C2 plus sometimes of C1, that is okay. Okay. Directly multiplying a ring, or sorry, a column or a row with a non-unit is not allowed. But linear relations you can put. Okay. So here also see minus 2 R1 is allowed. So that we can do. So that will reduce this 2 to 0 and 5 will be as it is. So now, and also this uh, 1 divides 5. Okay. So this condition is also satisfied. 1 divides 5. So diagonal entries are this first diagonal entry is dividing this second one. So this is also okay. So this is your Smith normal form for this matrix. And once you have a Smith normal form, so you can so this implies that your given matrix A is equivalent to this matrix 1, 0, 0, 5. So you can compute the column space of this matrix. Okay. And that will implies that Z square modulo the column space of A is would be isomorphic to the Z square, the column space of this matrix. Okay. 1, 0, 0, 5, this matrix. If you compute the column space of this matrix, it will give you the same. So we will compute the column space of this matrix. Okay. So columns, let us say that this is your AS. Column space of AS is a set of vectors. Uh, this is just AS times columns in Z square. Let's say it is x1, x2, such that this x1, x2 are varying in Z square. So this will be just, to multiply them, it is just x1 5 of x2 such that x1 and x2 are in Z, right? This is same. So what this column space is, the first entry is, or that is saying exactly like that. This is just alpha beta, where your alpha is varying over Z and beta is varying over 5Z, right? 5 times Z it is happening. So I am just replacing the variables. So this set is same as this set. Okay. So this is column space of AS, and that is also the same as the, oh, no, not exactly the same as column space of A. So this column space AS may differ with the column space of A. Okay. But the modulo Z square modulo of C of AS, that will be same as Z square modulo C of A. Individually, these C of AS and C of A may be different, but the modulo part will be same. So if you take the modulo, then it is uh, just see what is Z square. Z square is the set, uh, let me just write some AB such that A and B are varying over Z. This is your Z square, and with this you modulo, it's not the some module of it, that is the set of all tuples or column vectors alpha beta such that alpha belongs to Z and beta belongs to 5Z. Okay, so your first coordinate is varying over Z and you are modulo it. So in the first coordinate you will have 0, right? Because whatever you have over the Z in the modulo relation, you are moduling it. So the first coordinate will be moduled, will become 0, and in the second you are actually what this, if you look, just focus on the second coordinate. B is varying over Z, and here the second coordinate is varying over 5Z. So this is same as moduling Z with 5Z. ठीक है?
सर ये थोड़ा फिर से बता देंगे?
Yes. So see, Z square is simply the set of all column vectors with both the coordinates over Z, and its columns C of AS is the column space alpha beta such that alpha is varying over Z and beta is varying over 5Z. So you are modeling this space with this space, okay, with these relations. So alpha belonging to Z, and then A belonging to Z and alpha belonging to Z. So whatever first coordinate is, you are modeling it as it is. Okay, so that's why if you model the first coordinate, you will get 0 at the first coordinate, and in the second coordinate it is an integer that is moduled by the 5Z integer, means it is just Z and modulo 5Z. What are the elements in Z modulo 5Z? You look integers with the modulo relation 5 of 5Z, means uh, in modulo classes of 5, that is 1 bar is same as your uh, 6 bar, like 5 is 0 there. So that's what happening here. Multiple of 5 is 0, because you are modeling it means you are making it 0, the identity. So that's why the second coordinate will vary over Z modulo 5Z, because here the second coordinate was just 5Z. So you have to modulo it with this coordinate. So it is 0 times some, say you can say C, such that C is varying over Z modulo 5Z. Okay, just give a thought over it. You will definitely uh, realize why I am writing like that. So it is nothing but 0 direct product with z modulo 5z, and it is a finite uh, module. So the first option is definitely not correct. Okay, first is saying which of the following, for which of the following z square c is infinite. So first is not correct. You are getting a finite thing here. Okay, so we will see more such examples, and it will become clear to you. After that, we need to check all other options also, na. So let's pick the second option. Second option is 1423. So due to time restrictions, I am just writing the Smith normal form directly. The process is same. It is 1423. Okay. Or like if you want, then maybe one more we can compute, and then I will write it explicitly.
सर
So
वो फाइनाइट कैसे है वो बताएंगे एक बार पहले.
this is clear. This is equal to 0 cross z modulo 5z, or
यस सर यस सर.
then this is finite 0, यहाँ एक ही एलिमेंट है, एंड दिस इज जस्ट z मोडुलो 5z, z5 जो ग्रुप होता है, तो इसमें तो 5 एलिमेंट आएंगे ना. सो व्हाट इज द कार्डिनलिटी ऑफ दिस ग्रुप? 1 into 5, that is 5.
ओके सर गॉट.
ठीक है. द ट्रिक हेयर इज टू सी हाउ दिस modulo space is 0 cross z modulo 5z. Okay, so let us compute uh, the Smith normal form for this matrix also, and then I will start writing directly. You need to compute definitely. So see, we need to make this 4 to be 0. So C2 is just C2 minus 4 C1. If you do it like that, that will be 1 0 2 3 minus 8, that is minus of 5. Then you need to make this element to be 0. So R2 is R2 minus 2 of R1. This is 1 0 0 minus 5. This is also okay because 1 divides minus 5, so it is Smith normal form. If you want to remove minus 5, then you can also do that by just writing C2 is minus of C2. It will become 1 0 0 5. Okay, and that is exactly same as this. Okay, what, so they both have the same Smith normal form. Let I missed just a small step I missed. So this is same as this is same as z square c of a. So that's why z square, or isomorphic. So that's why this z square c of a is finite. Okay. So if you want to write this matrix as B, then this is Smith normal form. This is Smith normal form of B, but that is same as Smith normal form of A, right? So the column space would be same, and z square column space uh, uh, would be same. So all these things will follow as it is. So this will implies that z square normal C of Bs is z square modulo C of As, and as this is finite, so this will also be finite. Okay. So here also this option is not correct because we need to find which for which this is infinite. So let's move on to the third option. Okay. We are not computing again because is it exactly the same Smith normal form. See, Smith normal form for a matrix is unique, but two matrices may have the same Smith normal form. Okay. So in this case, the first and second option are
Yes,
giving you
sir.
the same normal form.
Yes, sir.
So we
Got it.
won't, okay, so we won't compute it again. Now let's see the third option, -1, 0, -3 and 2. -1, 0, -3 and 2. So here you already have 0, you need to make this to be 0. So it is easy to make this 0. You just need to write R2 going to R2 plus 3 times R1. So this is -1, 0. Oh, sorry, minus of 3 times R. Because -3 times -1 will become 0. So R2 is minus of 3 times R. So it will be 0, 2. Now you can keep it as it is because -1 divides 2, but if you want, you can also make this to be positive. So just replace R1 by minus of R1. It is 1, 0, 0, 2. And this is, if it is C, then this is your C of S. Okay, Smith normal form. Now you need to compute the uh, column space of it, and all these things you need to recheck. I think C is not a good notation because we are also using C of A. Let me write maybe D of S. So column space of D of S, it is just the image of it, 1, 0, 0, 2. You have x1, x2, and x1, x2 are varying over z, or you can say that x1, x2 is a vector in z square. Both have the same meaning. So now what is this? This is just the vector x1 2 times x2 such that x1, x2 are varying over z. Now this is same as the set alpha beta such that alpha is varying over z and beta is varying over 2z, right? Clear?
Yes, sir. Yes, sir. Right.
Okay. So now see the column space. This is column space. Now look at the modulo space, z square modulo c of ds, which is also same as the z square modulo column space of D, the original matrix, and that would be moduling this x1, x2 such that x1, x2 varying over z. This is your z square space moduled by under the relation that alpha beta such that alpha belongs to z and beta belonging to 2z. So you are moduling it with this relation, means whatever in see whatever again the same thing. If alpha is an integer, then you have to make it 0. That what this uh, uh, moduling means. Okay. Or if you are confused, then consider it as a kernel, and this is as the domain. Okay. Under the equivalence, this equivalence relation, you have to see this module. आई थिंक इसमें कंफ्यूजन था रवि पहले, ठीक है?
हाँ सर, एक बार फिर से थोड़ा बता देंगे सर?
ओके, सो हमें क्या करना है? वी नीड टू सी दिस सेट मॉडुलो दिस रिलेशन. So you consider it as a domain with this kernel. You need to see the elements of this set under this relation. So if alpha is an integer, you need to send it to 0. So here x1 is an integer. So if you send the first coordinate, so it will be directly sent to 0. So first coordinate will be 0. Okay. And second is you need to send it to 0 if it is uh, a multiple of 2. Okay, so consider it as a kernel, that the kernel of kernel uh, is this, and the original domain is this. So this modulo, this set is just 0, and you just take a different variable gamma, and such that gamma is belonging to z modulo 2z, because for each even integer you are sending it to 0. So the relations are modulo 2, right? So for modulo 2 element, you need to pick the element from z modulo 2z. वहाँ भी यही हो रहा था कि the element here you have alpha belongs to z or beta was in 5z. So multiple of 5 is 0 in after moduling it. So you need to pick the elements modulo 5. So if you are picking the elements modulo 5, then that those elements are nothing but the elements of z modulo 5z. Okay, or here it will be z modulo 2z. ठीक है, so this will be again 0 times z modulo 2z, and it is again a finite set. So it is also not infinite. So the only option remains is the last one, and that should be correct. But we will see why it is correct. Okay, because that will also give you an idea how this square modulo column space of a matrix is mm, infinite. How to do compute for that case. Okay, but the good thing for fourth example is it is already in a well in a nice form, in the Smith normal form. It is 2000, but is already there in that form. So we won't change it. We will keep it as it is and directly compute the column space and then the modulo space for it. So 2000. Okay, let this matrix be E. So column space of E will be nothing but the image of it with by the vectors in z square, that is x1 x2, such that x1 and x2 are inside z. So this would be nothing but 2 of x1 0, such that x1 is belonging to z, and as I said, it is same as alpha 0, such that alpha is inside 2z. Okay, now we need to see the modulo space. So again it is x1 x2, such that x1 x2 is inside z, modulo the space uh, alpha 0, such that alpha belonging to 2z. So see, in the second coordinate you are not changing anything. You are keeping the second coordinate, let's say this is of AB. Okay, so in the second coordinate you are not making any change, so second coordinate will vary over z, because you are not modeling anything. You are modeling uh, in the second coordinate there is nothing. So for second coordinate you are not modeling anything, so second coordinate will freely vary over z, because in the beginning it was varying over z. You are not imposing any condition over it, so it will still vary over z. But in the first coordinate it was varying over z, and then you modulo it with 2z. Okay, so that's why the first coordinate will be from z modulo 2z, and second will vary freely. Okay, so it will be z modulo 2z cross z. Now it is an infinite set, because this has cardinality 2, but it has cardinality infinite. Okay, so this is infinite. That's why the fourth option is correct. Okay, is it clear, Ravi?
Yes, sir. Got it.
ठीक है. The entire thing is about computing the column space and modulo it. So if it is clear, then let's move to the next question. I just paste it for you. Here it is. So it says given a prime P, a P group is uh, a group where the order of every element is a power of P. Okay. Now for which of the following matrices the quotient group Z square modulo CA is a P group. Okay. So now again the same thing we need to do, need to compute it for every matrices, and then we need to see that for which of the matrices the, it's a P group. But 5523 we have already checked. It is the same as yeah, the first option of it, right? First option of our last question. It was also 5523, and the group that came is 0 modulo 0 cross Z modulo 5Z. So for first option at least we won't do it again. So for this, by fourth part 1 Z square modulo CA, there was uh, 0 cross Z
Sir, I
modulo.
did not understand the question.
Okay, so it says given a prime P, a P group is a group where the order of every element is a power of P. Okay, so a group where each element has a order as some power of P. Okay, for a fixed prime P, like your Z4, the group of order, the cyclic group of order 4. There the possible orders is 1, 2, and 4. Okay, so 1 you can consider as 2 raised to 0, and then 2 is definitely 2 raised to 1, and 4 is 2 square. So each element has an order that is some power of 2. So that's why your Z4 is a 2 group. Okay. Similarly, you can consider other groups like Z8. In Z8 also the possible order is 1, 2, 4, and 8. All these are powers of 2, and 2 is a prime, right? So your Z8 is also a 2 group. Okay. So this is what the definition of P group is. Then the question is, which of the following matrices, for which of the following matrices A, this your the group Z square modulo CA. The same thing we were computing in the last question. A P group. In the last question, we need to check that for which of the matrices A, this Z square modulo CA is infinite, right? And in this question, we need to check that for which of the matrices A, this Z square modulo CA is a P group. Okay.
Okay. Yes, sir.
So we
Prime
have
group
already
we
come.
will find. There,
Huh?
in previous question we found the infinite. Now here we will find
Infinite or fine.
which one is prime.
Which
Prime
one is
group.
P group?
Hmm.
Huh. Okay. So Z square C here we have already computed with this for this matrix in the last question. So there it came to be 0 cross Z modulo 5Z. Okay. And that is same as, see, up to isomorphism, that is same as Z modulo 5Z, right? Now, now Z modulo 5Z has uh, each, the possible order is 1 and 5 in Z modulo 5Z. And both these are powers of 5, 5, 0, 5 raised to 0, and 5 raised to 1. So in this case, it is a 5 group, right? It is a P group for P equal to 5, right? So this is the first option, and the next three also we will check, and for this we need to again compute what we were computing before. The second part is uh, A6880. So I'm not uh, computing the Smith normal, means I'm just writing it. You can also verify, okay, because we have already seen enough examples of it. So the Smith normal form of it will be 20032. Okay, the same way we did earlier. Now you just need to follow the same steps, and you will compute this. You will end up with this Smith normal form. And let's say this is your AS. So C of AS is just 20032 times x1 x2, such that x1 and x2 are in Z. Okay, so this will be 2 of x1, 32 of x2, such that x1 x2 are in Z, and that will be same as alpha beta, where alpha is in 2Z and beta is in 32Z. Okay, now compute the modulo space, that is x1 x2, such that x1 x2 belongs to Z, modulo alpha beta such that alpha belongs to 2Z and beta is in 32Z. This we need to compute. So same thing, in the first coordinate we are given that x1 is varying over Z, but we need to see the it modulo 2Z, and in the second x2 is varying over Z, but we need to see it modulo 32Z. So it will just be gamma delta, such that gamma is varying over Z modulo 2Z and delta is varying over Z modulo 32Z. ठीक है, and that is Z modulo 2Z cross Z modulo 32Z. Okay, so here the element, each element is having order as some power of 2, and here also each element is having order as some power of 2, right? Maybe Z modulo 32Z, all elements will have power order either 1, 2, 4, 8, 16 और 32. ठीक है, सारे पावर्स ऑफ 2 है, एंड हियर
Yes,
आल्सो यू
sir.
हैव ऑल पावर्स ऑफ 2. तो इनके जब डायरेक्ट प्रोडक्ट होगा, एंड ऑर्डर ऑफ एलिमेंट इन डायरेक्ट प्रोडक्ट से a कॉमा b इज ऑर्डर ऑफ a टाइम्स ऑर्डर ऑफ b. ठीक है, सो ऑर्डर ऑफ a इज सम पावर ऑफ 2 एंड ऑर्डर ऑफ b इज सम पावर ऑफ 2. तो जब इस टपल का ऑर्डर निकालेंगे, दैट विल अगेन बी सम पावर ऑफ 2, राइट?
Yes, sir.
So it is a 2 p group, right? For p equal to 2. Okay, so this is a p group for p equal to 2. Okay, okay. So now let's move to the third part, 3690. So again, I am not computing this Smith normal form, I am just writing it explicitly. 3690. So this is equivalent, let's say this is your A now, and it will be, the Smith normal form for it will be 30, 0 18. ओके, यहाँ पे 6 है, सो जस्ट माइनस इट टू ट्वाइस ऑफ 3, एंड यहाँ 9 है, जस्ट माइनस इट ट्वाइस ऑफ 3. बट इन दैट प्रोसेस दिस 0 will be changed to -18, and then minus you can remove, so we will get 18. Okay, so this is your Smith normal form, that is say A of S, and C A of S. In the similar way, what will you get? Here you had 232, तो Z2, तो ये सेट आ रहा था अल्फा बिलोंगिंग्स टू 2Z, बीटा बिलोंगिंग टू 32Z. मॉडुलो करने के बाद क्या आया? Z मॉडुलो 2Z एंड Z मॉडुलो 32Z, क्योंकि 2 और 32 था, यहाँ 3 और 18 है. सो व्हाट विल बी द क्वोशिएंट स्पेस?
3 का हो जाएगा सर, 3 प्राइम का टपल होगा.
So the column space will be Z square C of AS, that is also same as Z square C of A. It will be just Z modulo 3Z cross Z modulo 18Z, right? Similarly 318 की जगह 232 था यहाँ पर, as it is we will follow it, and then Z modulo 2Z, we, in place of it we will get Z modulo 3Z, and Z modulo 32Z we will get Z modulo 18Z. Okay, but this is not a P group. See, this Z modulo 2Z is same as Z modulo 9Z cross Z modulo 2Z, right? Because 9 and 2 has the same GCD.
Yes sir,
Sorry, has GCD 1.
same as,
So this has GCD 1. So this is Z modulo 3Z cross Z modulo 9Z cross Z modulo 2Z. So यहाँ it has it will have element of order 2 also. It will have element of order 3 also. Okay. Here see your 1 0 0. What is the order of this? The order of this is 3, right? Because 1 is from Z
yes
modulo
sir,
3Z, and order of 0 1 sorry 0 0 1 is, yes, 1 is from Z modulo 2Z now.
yes sir, from Z modulo to Z.
So it is 2, right? So they are not powers of the same prime, right? So it is not a P group. Clear? For P group, each element must have the order as some power of P, and the T is fixed. Okay, here you are getting two different primes, 2 and 3. They are not power of the same prime. So that's why it is not a P group. So in case of third, we won't get a P group. Now let's move to the last option, that is 5205. So fourth option is 5205. ठीक है, I am again writing its equivalent matrix as it is. So the equivalent matrix is 1 0 0 25. ठीक है, and if you compute the column space of it, then column space of this is say A, this is say AS, column space of AS is going to be 1 0 0 25 x1 x2 such that x1 and x2 are varying over Z. ठीक है, this is x1 25 of x2 This is x1 25 times x2, x1 x2 varying over z, and that is same as alpha beta, alpha varying freely over z and beta is varying over 25 of z. ठीक है. So if you modulo it with z square c of as, then in z square the first coordinate is varying over z and you are modeling it. So in the first coordinate you will have 0. Okay. So in the first coordinate it will be 0 and second coordinate is varying over z and you are modeling 25 multiples of 25. So it will be 0 times gamma such that gamma is varying over z modulo 25z. So this is 0 cross z modulo 25 of z, which is same as z modulo 25 of z, and z modulo 25 of z is a p group because possible orders are 1, 5, 5 and 25. So it's a p group for p equal to 5. Okay, so it is the completion of our fourth or fifth question. Fifth question. So is there any doubt, or we can move to the next question?
Yeah, correct, sir. Got it.
Okay, so let's see the next question. Question number 6. Okay. Okay. So it says that now an elementary abelian group is one in which every element except the identity has order p. Okay, exactly order p, not some power of p. Exactly the order is p except the identity element. Okay, for some prime p, and that prime is fixed. For which of the following matrices? Now we need to check that this group is an elementary abelian group. So example of elementary abelian group is you can take z modulo 2z, that is in this each element has order 2 except the identity, दो ही element है. And you can also take z modulo 2 z cross z modulo 2z. Here also the element has order 1 for identity and then all other have order 2. Or you can take many direct product as you want with z modulo 2z. Similarly, z modulo 3z, 5z, 4z you can take. But z modulo 2z cross z modulo 4z, that is not elementary abelian. It's a p group, but it's not elementary abelian because here you have one element of order. Here you have more than one element, in fact, of order 4. Okay, so elementary abelian groups are uh, subclasses of p groups. Okay, and you can see or realize the fact using the fundamental theorem of abelian groups, finite abelian groups, that any elementary abelian group is of this form: z raised to pz cross z raised to pz. Okay, it's a direct product of some uh, z modulo pz for fixed prime p. So z modulo 3z is an example, 2z direct product of z modulo 2z is an example, z direct product of 3z is an example, and these are the only examples, the direct products of cyclic p groups for the same prime p. ठीक है? Is the definition clear?
Yes, sir.
Okay, so ठीक है. Let me just erase it. So 5523, we have already seen this example before as well. Same example ऊपर भी देखा था. In question number 4, 5523, yes, it is just z modulo 5z. So I will not solve it again. It is same by fourth first part. it has z square Ca to be just isomorphic to z modulo 5z, and it is a p elementary abelian group, right? Elementary, we all we already see what are the possibilities. Elementary abelian 5 group, ठीक है? And this 2000, this is also an example in your fourth question. In fourth question it was an option, the fourth one. Here you got the group to be z modulo 2z cross z, z modulo 2z cross. So by fourth part, fourth, in this case you have z square Ca to be z modulo 2z cross z. Okay, it is an infinite group. It need not. It's definitely not an elementary abelian group, because here the order is infinite, which is not a p, right? Or you can, yes, this is an infinite group.
Yes, sir.
This is an infinite group, so not an elementary abelian group. Elementary abelian group. ठीक है? So now let's see the other two examples. For that, again, we need to compute this z square Ca part, and I will write directly the Smith normal form, and then uh, you can check that it should be what I computed. It is 3214. So the Smith normal form of it is, just give me a second. It is coming out to be 1. It is equivalent to 1 0 0 10. Okay, so देखो यहाँ ऊपर वाले पार्ट में 1 0 0 25 था. So what you got, 0 cross z modulo 25z. So instead of 1 0 0 25, you have 1 0 0 10. So it will be 0 cross z modulo 10z. Same process we will follow. So this will implies this is your as z square C of as is 0 cross z modulo 10z, and that is similar to fifth, fourth part. Okay, same thing, right? And that is same as or isomorphic to z modulo 10z, and but this is isomorphic to z modulo 2z cross z modulo 5z. Different primes are coming, so it's not an elementary abelian P group. Even it's not an P group. Elementary abelian P group. So, is it clear? Okay. So now let's see the third option. 1, 2, and 4 we have seen. Third is 20, 15, 5, 5. 20, 15, 5, 5. This is equivalent to, just write it directly, it is equivalent to 5, 0, 0 5. Okay, so similar to your this example 30018, if you compute it, it will become z. Here you will getting z mod 3z cross z mod 18z. Here you have both entries to be 5, so it will be z mod 5z cross z mod 5z. So I'm just writing it similar to fifth third part. Okay, similar to fifth third, you can compute that this is a, this is as, c of as is z modulo 5z cross z modulo 5z, and it is a direct product of same cyclic p groups, so it is elementary abelian, right? This is
Yes, sir.
elementary abelian 5 group. Okay, fourth option we have already seen, so that concludes the question. Is it clear?
Yes, sir, correct.
Okay, so these three questions demanded just the computation of z square modulo CA. Okay, so we have done enough questions like that. So now let's move to the seventh question. Seventh question is a question of different nature, entirely different nature, and I think you might have done these kind of questions before. So it says up to isomorphism, how many finite abelian groups of order 280 are there? So
सर प्रीवियस क्वेश्चन का आंसर तो ये लास्ट वाला हो जाएगा ना?
हाँ, एक ये फोर्थ थर्ड वाला हो जाएगा, एंड सेकंड इज नॉट देयर, फोर्थ इज नॉट देयर, एंड फर्स्ट वन आल्सो. Okay, first and third, there are more than one options correct.
ओके ओके सर.
Okay, so the last question is up to isomorphism, how many finite abelian groups of order 280 are there? So uh, number of, so 280 is in prime decomposition. If you look at it, then 280 is just uh, 5 into 7 into 8, and that is 5 into 7 into 2 raised to 3, or 2 raised to 3 cross. This is the prime decomposition of it. Okay,
Yes, sir, I did.
so on the fundamental theorem of finite abelian group says that number of finite abelian groups of order n is just, if you decompose it in primes, then partitions of the power of primes. The number of finite abelian groups of 280 is just, here the prime is 2 and its power is 3. So partition of 3 times partition of 1 times partition of 1. If n is uh, say p1 alpha 1, p2 alpha 2, so on to pk alpha k, the number of finite abelian groups of order n, definitely up to isomorphism, that will be just partition of alpha 1 dot partition of alpha k. Okay, so here partition of 3 times part 1 times part 1, and how many partition of 3 are possible? First is 3, then 1 plus 2, and then 1 plus 1 plus 1. integer partitions. Okay, that implies P of 3 is 3. And for 1 you have only single partition, that is 1. You can't break it in more than that. So partition of 3 is 3, 1 is 1, 1 is 1. So there are only 3 such groups. Okay, and even if you can see what are those groups. So Z5 cross Z7 cross Z8, and as the breaking is there in 3 only. Okay, so just break powers of 2 cube like that, powers of 1. So this is 2 cube. This is the first possibility. The second possibility is Z5 cross Z7. Now break 3. So power of 2, that is, and that is 2 plus 1. Okay, so Z4 cross Z2 आ जाएगा लास्ट में. And the third option is 1 cross 1 cross 1. That is Z5 cross Z7, Z2 cross Z2 cross Z2. ठीक है, these are the 3 abelian groups up to isomorphism for order 280. ठीक है, is it clear?
Yes, sir. Got it.
Okay, so if that is clear, then let's move to the last question of this tutorial and also this course from my side. Uh, so that is, let me just change the page first. It says, and let n1 be the number of abelian groups of order 128 and n2 be the number of abelian groups of order 432. Then what is the relation between n1 and n2? Okay, is n1 greater than n2 or n2 greater than n1, or they are same? So let's see. So the same thing we will do. We will partition. We will see the prime factorization of 128. It is 2 raised to 7 that you can see, and the prime factorization of 432. So for 432, it is 2 raised to 4 times 3 raised to 3. Okay. Now partition of 3, 4, and 7, you need to see. They are giving you the partition that there are 15 partition of 7. This is already given. You can also check what are these 15 possibilities, and corresponding to each partition you will get a abelian group, right? The way we did it here. Okay, 3 के जो जो partition थे उसके corresponding एक एक group हमें मिल गया, right? और बाकी जो थे वो as it is same चले. So ये 3 के partition थे, corresponding हमें ये जो डायरेक्ट प्रोडक्ट वाला पार्ट था वो मिला. ठीक है, सो ये हमारा ये 3 पार्टीशन थे 3 के. So corresponding to these 15 partitions you will get 15 abelian groups. So this is equal to n1. Okay, and for this n2 is partition of 4 times partition of 3. ठीक है, partition of 3 we already computed. Partition of 3 is 3, ये हमने already देख लिया है. Now let's check what is partition of 4. For partition of 4 it is 5, and you can check it in the rough. First keep 4 as it is, break it into 2 parts, 1 plus 3, 2 plus 2. Now try to break it in 3 parts. The only possibility is 1 plus 1 plus 2. And try to break it in 4 parts, and it is 1 plus 1 plus 1 plus 4. So these are 5 partitions of it. So P4 is 5. So N2 is P4 times P3, that is 5 into 3, that is 15 again. And that implies that your N1 is same as N2. ठीक है? So is it clear?
Yes, sir.
Ravi? Okay, so is there any doubt in the entire lecture If it is, then you can ask now. Otherwise, we will stop it here. Clear?
सर एक बार क्वेश्चन ये दिखाइए, क्वेश्चन दिस लास्ट वन.
एट्थ वाला ये
ओके सर, गॉट.
ओके.
हाँ
सो
सर.
ठीक है. So this is our last tutorial. So okay, then I'll stop it here. So I can just write my mail ID here. If you
Yes sir, your mail ID. And sir, in future if I get some doubt or question, please respond there. I will put question or
ha ha
something.
ha, you can mail me here. Yes. Great. Okay. You can note it down also. Otherwise, this will be there in the recording as well. Okay. I will upload it with notes also, so you can see from there as well. ठीक है रवि.
जी सर, बहुत बहुत
ओके.
धन्यवाद सर.
Okay, it's fine. So let's stop it here.
हाँ.
ठीक है. Okay then. Thank you.